Physical Review A, Volume 39, Number 5, March 1st, 1989, Gravity as a Zero-Point Fluctuation Force. H. E. Puthoff, Institute for Advanced Studies at Austin, Texas, 78,746, received March 14, 1988, revised manuscript received August 15, 1988. Sakharov has proposed a suggestive model in which gravity is not a separately existing fundamental force, but rather an induced effect associated with zero-point fluctuations, ZPFs, of the vacuum, in much the same manner as the van der Waals and Casimir forces. In the spirit of this proposal, we develop a point particle, ZPF interaction model that accords with and fulfills this hypothesis. In the model, gravitational mass and its associated gravitational effects are shown to derive in a fully self-consistent way from electromagnetic ZPF-induced particle motion, Zitterbewegung. Because of its electromagnetic ZPF underpinning, gravitational theory in this form constitutes an already unified theory. Introduction. Gravitational theory, whether in its scalar Newtonian form or its tensor general relativistic form, is recognized to be essentially phenomenological in nature. As such, it invites attempts at derivation from a more fundamental set of underlying assumptions, and 6 such attempts are outlined in the standard reference book Gravitation by Misner, Thorne, and Wheeler, MTU. Of the 6 approaches presented in MTU, perhaps the most far-reaching in its implications for an underlying model is one due to Sakharov, namely, that gravitation is not a fundamental interaction at all, but rather an induced effect brought about by changes in the quantum fluctuation energy of the vacuum when matter is present. In this view, the attractive gravitational force is more akin to the induced van der Waals and Casimir forces than to the fundamental Coulomb force. Although speculative when first introduced by Sakharov in 1967, this hypothesis has led to a rich and ongoing literature on quantum fluctuation, induced gravity, that continues to be of interest. In this approach, the presence of matter in the vacuum is taken to constitute a kind of set of boundaries, as in a generalized Casimir effect, and the question of how quantum fluctuations of the vacuum under these circumstances can lead to an action and metric that reproduce Einstein gravity has been addressed from several viewpoints. These are treated in some detail in a comprehensive review by Adler on gravity, as a symmetry-breaking effect in quantum field theory. On the basis of heuristic and dimensional arguments along general relativistic lines, Sakharov argues that in a vacuum fluctuation model for gravity, the Newtonian gravitational constant g should be determined by an expression of the form g 11/2, where it corresponds to an effective Planck cutoff frequency of the vacuum zero-point fluctuation ZPF spec trum. In this approach, the small, but finite, value of the gravitational constant is an inverse reflection of the high, but not infinite, value of the high-frequency cutoff of the ZPF. In this paper we explore the Sakharov viewpoint on the basis of a conceptually simple classical model, but including ZPF, in which matter, in the form of charged point particles, partons, interacts with the ZPF of the vacuum electromagnetic field. As part of this development, the model predicts 1. To be precisely of the form G equal to WdAg. In order to constitute a self-consistent viable basis for gravitation, however, a first-order ZPF model for gravity must provide not only a basis for calculation of the gravitational constant G, shown to reflect the ZPF cutoff, but must also account for the genesis of the gravitational mass and the attractive inverse square law force. In the particular version of the Sakharov hypothesis pursued here, the mass is shown to correspond to the kinetic energy of ZPF-induced internal particle, parton, motion, ZPF jitter, or Zitterbewegung, while the force is found to be of a long-range retarded van der Waals type, associated with the broad-spectrum ZPF radiation fields generated by that same Zitterbewegung motion. To arrive at the above results, basically, we simply assemble together in a straightforward fashion previously published results regarding ZPF models of van der Waals and related effects in flat space-time. When this is done, one finds the leading term in the interaction potential, previously unexamined, to be Newton's law with no free parameters to be fixed. In such a fashion, the identification of this term as gravitational emerges naturally from the concatenation of the previously published results. Yet further evidence for the correctness of this interpretation is provided in SEC. 6. Where details of the pattern that emerges are presented in the context of a self-consistent, coherent picture of the underlying dynamics of the gravitational force that conforms to the facts as we know them. 39,333. 1989, The American Physical Society. 2,334. 39. Second vacuum ZPF electromagnetic fields, Ref 8. In the classical approach used here, point-particle, ZPF interactions are treated on the basis that charged point-mass particles interact with a background of random classical electromagnetic zero-point radiation with energy spectrum, as in the quantum mechanical case. P, W, dW2 hectares, or dU2, where the first factor in parentheses corresponds to the density of normal modes, the second to an average energy per mode. This treatment of quantum field particle interactions on the basis of a classical ZPF constitutes an analysis technique known in the literature as stochastic electrodynamics, SED. SED is a well-defined framework that has a long history of success in yielding precise quantitative agreement with full QED treatments of such topics as Casimir 10-12 and van der Waals forces, topics directly related to the one pursued here. In this approach appears in the above expression simply in the role of scale factor, without need of quantum interpretation, and all other appearances of in the development can be traced back to its appearance in this expression. The spectral energy density represented by 3 formally diverges as W3. It is generally assumed, however, that the spectrum is effectively cut off at a frequency roughly corresponding to the Planck frequency. As we shall see in the following sections, this assumption is supported by the line of development presented here. As a first step toward developing the hypothesized underlying ZPF basis of the gravitational interaction, we compare the forms of the spectral distribution of the ZPF of the electromagnetic fields as seen from unaccelerated and accelerated frames of reference. Of particular significance with regard to the spectral distribution in an unaccelerated frame, given by 3, is the fact of its Lorentz invariance, which derives specifically from the spectrum's cubic dependence on frequency. The cubic spectrum is unique in its property that delicate cancellations of Doppler shifts with velocity boosts leaves the spectrum Lorentz invariant. 4. In an accelerated frame, on the other hand, the detailed balance of Doppler shift cancellations is negated, with the result that the spectral distribution takes the form 15. 2 PLO do equal to 1 plus C plus 2 KHXP, 2 RCO, A minus 1. Where A is the proper acceleration relative to a Lorentz frame. This expression was originally derived by Boyers on the basis of the random classical ZPF background assumed here. The purpose was to derive a result, first obtained by Davies and Unruh within the context of quantum field theory, which showed that, apart from an additional density of states factor, 1 plus, the spectral distribution seen by an accelerating observer assumes a thermal Planck form if one makes the identification T equal to He, 2 MCA, K is Boltzmann's constant, T, absolute temperature. In commenting on the additional density of states factor, Boyer points out that the additional contribution beyond the thermal Planck form is related to the space-time properties of an accelerating reference frame. This gives us a clue that, via the equivalence principle, this additional term can be related to the gravitational interaction. Of special interest here, therefore, is not the thermal term of interest in the original treatment, but rather the leading terms. P, W polar, plus AP, W equal to plus. These indicate that an accelerated observer would see the background ZPF spectrum augmented by a term proportional to the square of the acceleration. Application of the principle of equivalence then indicates that the additional spectral contribution seen in a frame with acceleration A should also be seen in a non-accelerated frame with local gravitational field 8, produced by a gravitational mass m setting G equal to S-1 gm R2 we obtain. AP equal to 225 gmg. Thus, the principle of equivalence predicts an additional contribution to ZPF energy by gravitational mass, a requirement that must be met in any ZPF-based theory of gravitation. Since this additional contribution of energy is electromagnetic in nature, we must ascribe to mass an appropriate electromagnetic field-generating function, a point to which we return in SEC. Third, Zitterbewegung model. As our basic point, particle, ZPF interaction model, we represent matter as a collection of charged point mass particles, partons, in accordance with standard theory. In the development that follows it, it's not necessary to invoke the details of particular parton representations, for example, families of fractionally charged quarks, beyond certain general concepts, such as the asymptotic freedom of partons to respond to the high-frequency components of the ZPF spectrum as essentially free particles. It is necessary to focus to the charged parton level, however, in order to represent properly the essentially equal magnitudes of proton and neutron contributions to gravitational mass. This accounts for the fact that charged and neutral matter participate equally in the gravitational interaction based on underlying charged parton interactions. We begin our discussion of particle field interactions by examining the properties of a simple charged harmonic oscillator of natural frequency A, corresponding to a binding force that is linear in displacement from equilibrium, located at the origin and immersed in 0 point. 39. Gravity as a zero-point fluctuation force. 2335. Radiation. The non-relativistic equation of motion for a particle of mass μ and charge q, including radiation damping, is given by μ plus m(or). If we introduce the dipole moment, P equal to Qr, and the damping constant, R equal to Q2, Bromach 3, we can write 7 in a form convenient for later discussion. P plus Wp equal to Tb plus 6 ReC3 TeZp. We will also be particularly interested in the kinetic energy, MOT, which becomes 12TeC3R. Once written in this form, the oscillator equation of motion, 8, and energy equation, 9, refer only to the global properties of the oscillator, dipole moment P, natural frequency, and damping constant I, and do not involve individual mechanical properties of the oscillator such as charge or mass. With regard to the ZPF fields, the vacuum is assumed to be filled with a random classical zero-point electromagnetic radiation whose Fourier composition underlies the spectrum given in 3. Written as a sum over plane waves, the random radiation, which is homogeneous, isotropic, and Lorentz invariant, can be expressed as 2 Espia T equal to ReZD 3 key 11 halves, 11 halves HP, R, T, ReD 3K, X2, 1 to 0 840 XL, X plus 1, K, where 1, 2 denote orthogonal polarizations and are orthogonal unit vectors in the direction of the electric field polarization and wave propagation vectors, respectively, K, are random phases distributed uniformly on the interval 0 to 2, independently distributed for each K, O, and A. It is at this point that we need to consider the correspondence between the above equations and the parton, ZPF interaction of interest. First, we treat the parton as a two-dimensional rather than three-dimensional oscillator, drawing on previous studies that model spin as the internal angular momentum associated with two-dimensional Zitterbewegung motion. Second, because we are interested primarily in the particle's high-frequency Zitterbewegung response to the ZPF, whose spectral density increases as a 3, we may to first order neglect the binding force term involving WO, asymptotic freedom, as it relates to the ZPF. Finally, we also neglect the radiation damping force in comparison to the inertial force and ZPF driving terms. Alternatively, the restoring force and radiation damping terms can be carried through in the derivations that follow, and appropriate approximations introduced at the end, without change of result. To obtain the expectation value of kinetic energy of the Zitterbewegung motion given by 9, 6, p. 12 mr, we follow a procedure due to Rueda. Under the asymptotically free particle assumptions stated in the paragraph above, the x component of 8 takes the form with a unit vector in the x direction. dp H is 11 halves equal to 6 13 T, easy P equal to 6 3 RD 3K 2 to 2 dt. Integrating once with respect to time, we obtain Px6 rec, reti FD 3K 2 to 2 equal to 6 me, RED 3K. 11, 2 to 10. The expectation value P then follows from 1 half 11 halves has who, 8 euros, IW XP, IK, R plus I0, K, O minus 10. Conjugates and the notate stems from the use of exponential notation. Equation 14 can, however, be simplified to P2 equal to 363 deg 3, D3K 8 to 8 to 1, psi 8 to 1, where averaging over random phases involves the use of exp I K2, R plus 10 K A 0K equal to 883 KT, with dk 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 K2, and the angular integration in K taking the form equal to FDN 1 K2 3 equal to 4. We can rewrite 15 with a change of variables to key as 2 equal to 1263 R to 1 cos 12 firsts plus A cost 7 sin A R. Where is the assumed cutoff frequency to be determined later? 21 4 P reaches the value for the two-dimensional Zitterbewegung motion assumed P2 equal to TO2, P2 equal to 12 euros 3R22, which when substituted into 9 yields 6 go 21. It is thus seen that the expectation value of the kinetic energy of Parton's Zitterbewegung motion reaches a finite magnitude, limited by the finite value of the, as yet undetermined, ZPF cutoff frequency. The energy calculated in this way is in the nature of the so-called transverse self-energy, in QED, of a particle in response to the electromagnetic zero-point fluctuations of the vacuum. Since the energy associated with this Zitterbewegung motion is an internal particle energy, that is, not directly observable, we identify this energy as that corresponding to the rest mass energy of the particle, m equal to 6 gon 22, as will be shown in SEC 4W, Me3, G12, in which case 22 reduces to GeG 23. In this view, the particle mass m is of dynamical origin. Originating in Parton, motion responds to the electromagnetic zero-point fluctuations of the vacuum. It is therefore simply a special case of the general proposition that the internal kinetic energy of a system contributes to the effective mass of that system. This derivation of mass as an internal kinetic energy of motion is thus the first result derived from the Zitterbewegung model. As will be shown in later sections, it is this mass that is involved in the gravitational interaction. Fourth, Zitterbewegung fields. We turn our attention now to the fields generated by the ZPF-induced Zitterbewegung motion. Considering, say, the x component of motion, we find that an assumed E time dependence substituted into 8 yields for the magnitude of any particular frequency component. P0 equal to xp, where the overtilt designates the magnitude of a frequency component, and once again we have neglected the binding and radiation damping forces. This expression can then be combined with the ZPF field expressions, 10 and 11, and the standard oscillating dipole formulas, EW re alpha p epsilon rho, GP, 1, A, equal to re B4, to yield expressions for the dipole fields generated by the Zitterbewegung motion, viz. E, re sigma alpha kappa 4 euros H, re 4.5 11 halves, plus, where, with a unit vector in the direction joining the dipole to the field evaluation point, 39. Gravity as a zero-point fluctuation force, 2337, 1 plus, 32 P2 minus 2, Kr 3 Kr 2 degrees Fahrenheit equal to Kx I plus Kr 2. The energy density in the dipole field distribution can be calculated from 27 and 28 as Awa equal to E, greater than plus H2, 12.2, equal to Re alpha P omicron, 11.2.5 Fes, S4 dead, 210 times, or G or 3xp, plus 10, K, O, minus 10, K. 2012 Fu 860 11 halves or 12 He, 8x, 2 to 2, 2 to 2, F2xp, A, plus 10, K, minus 10, K. This reduces to Org da, or F or 2 plus or G or 2, 3 R 16 square meters, deg 20, where we have made use of 17 and have averaged over random phases by the use of xp, A, plus 10, K, O, minus 10, K, 888 kk. The part of the integrand in parentheses in 32 can be evaluated by means of 29 and 30 and yields 2 sin kr 2 plus 4 cos 4 sos 2 plus sin 2 kr where is the angle measured from the dipole motion unit vector to the evaluation point unit vector. The first term proportional to 1/2 constitutes the radiation field associated with the ZPF-driven dipole. As shown previously by Boyer, this radiation just replaces that being absorbed from the background on a detailed balance basis with regard to both frequency and angular distribution, and therefore does not result in an incremental change to the background. Of the two remaining, induction, field terms, the R term predominates at large distances and is therefore the one of interest here. Designating the term of interest by a prime, we have 3cl2 cos 2 4 square meters deltioto micron SWW. This expression, obtained on the basis of considering a single x component of motion, must be doubled to take into account the contributions of the two independent degrees of freedom in the model. This leads then to an overall spectral density, a paler, equal to 24. Since in the final analysis we are interested in the net contribution of a large collection of randomly oriented individual particle motions, we average over the solid angle to obtain Apple, AP2R sine 22, since according to 22 there is a relationship between I and the particle mass m for ZPF-driven Zitterbewegung motion, 37, can also be written. APGLA equal to 2. Zitterbewegung motion therefore leads to the generation of an electromagnetic field distribution in proximity to the mass that is proportional to frequency times mass squared, divided by r, and upon detailed examination is found to be half electric, half magnetic. According to 6, moreover, a field of just this form is required by the principle of equivalence. Under the assumption that the gravitational and rest masses are identical, m equal to m, 6, and 38, can be equated to obtain the cutoff frequency, 11 halves r, which satisfies the Sakharov condition, 1, in terms of the cutoff frequency, we, 39, can be inverted to yield the gravitational constant g in the form of the second, non-independent Sakharov condition, namely TT2. We see, therefore, that the principle of equivalence requires a certain modification of the ZPF background by gravitational mass, and that the Zitterbewegung model of mass implies a similar modification. Furthermore, the compatibility of the two conditions on a precise quantitative basis requires only the equivalence of gravitational. 2338. H. E. Puthoff. 39. And rest masses, and a limiting cutoff frequency for the ZPF background on the order of the Planck frequency. This specification of the cutoff frequency W2 and its relationship to the gravitational constant g is thus the second result derived from the Zitterbewegung model. Thus we have a derivation that yields the relationships postulated to exist in dynamical scale invariance breaking models of gravity as a symmetry breaking effect. Fifth, gravitational force. The derivations in SECs. 3 and 4 dealt essentially with the characteristics of single masses. In this section we investigate the interaction between two such masses. The starting point is equations of the form 8, written for two masses, but modified to take into account the fact that each mass experiences not only the background ZPF field, but also the ZPF-driven dipole field of the other mass. The procedure followed here is precisely that developed by Boyer for the derivation of the retarded van der Waals forces at all distances between a pair of polarizable particles. Therefore, we need only outline the procedure, as it applies to our case. Two masses A and B, taken here to be equal for ease of discussion, are assumed to be located at positions ρ tg, respectively, with B located a distance r from A, along the positive z-axis of a coordinate system centered at A. The equations of motion, generalized from 8, take the form plus 6 euros 3 TE 1, plus 6 3 TE 1, 1, where ERT is the dipole electric field at the position of particle A due to the motion of particle B, and so forth. As in the derivations of previous sections, an assumed Elliott time dependence yields, for the magnitude of any particular frequency component, equations of the form D plus P equal to 6 euros 1 C3 T EZR, WRG, and similar equations for the Y and Z components where D equal to W2 plus 2 IGW3, 1I1 plus, KR, KR3, I1 plus, KR2, KR3. The latter expressions for N, etc., are derived for the geometry under consideration from the dipole expressions 25 and 29, consistent with the assumptions of previous sections. We neglect the binding and radiation damping terms in and I in 45. Furthermore, on the scale of interest in gravitation, distance is large compared with the wavelengths of the predominant Zitterbewegung frequencies. In calculating the force, we retain only the radiation field term 1, Kr. With these assumptions, 45, 47 become DRAD 2, Kr 0. Solutions for X and Pax are obtained straightforwardly from 43 and 44, subject to the conditions 48 and 49. It is then necessary to construct from these solutions the appropriate van der Waals forces between the pair of particles A and B. From classical theory, the force on a dipole is given by F equal to PV E plus PXB dP dt. Following Boyer, we note that the time-averaged force can be transformed as dP F equal to PVE plus dXB dt equal to PVE plus PX VXC, where the transformation of the second term, PXB equal to XBdR, follows from an integration by parts and substitution from Maxwell's equations, noting that the endpoint terms do not contribute to the time average. Manipulation of the vector operators in 51 then leads to the relatively compact form F equal to PV plus PV plus PV. One further reduction is possible. The symmetry of the geometry dictates that the average force on a dipole is along the z-axis joining the two particles. Therefore, the expression for the average force finally simplifies to F equal to F2 equal to P2 equal to AX as plus P2 plus pi as G as. In determining the average force on, say, dipole B, we must keep in mind that the electric field at B consists of both the background ZPF field and the dipole field due to particle 4, so that, for example, the first term in 54 becomes Pax RT equal to Pax Es 1 plus P, and so forth. The mathematics of carrying out the averaging then proceeds term by term, as in Ref 27, using, as in previous sections, the RE and complex conjugate notation. 39. Gravity as a zero-point fluctuation force. 2339, including averaging over random phases. The result for the special case of interest here, radiation field only, binding and radiation damping forces neglected, is in terms of the potential U29. Do 2 rands. The only difference here as compared to the derivation in Ref 27, aside from the specialization to the radiation field term, is the use of a finite cutoff frequency. This result is derived here and in Ref 27, on the basis of point particles interacting with a classical zero-point field. For those who might be more familiar with standard quantum calculations, this result has also been obtained by Renner from quantum electrodynamic calculations using a non-relativistic quantum oscillator model, and by Casimir and Polder using fourth-order perturbation theory in quantum electrodynamics. Equation 56 was derived for the case in which 3 degrees of freedom for particle motion are assumed. For the two-dimensional Zitterbewegung motion assumed in our case, n equal to 2, Geometrical considerations require that U be reduced by a factor, n32, see Appendix A. With this taken into account, the solution 256 becomes U21, cos 29, R322 sin R, where Y equal to W1RR equal to C, with the potential thus defined, the force is obtained from F equal to OR. We see therefore that the potential has the desired one. R dependence required for gravity, modulated by a fine structure overlay of the form sin R, 2, which has a spatial periodicity characteristic of the cutoff, Planck, frequency, 10 to 3 cm. If we extract the leading, non-oscillatory term, we find for the potential and force U equal to tar F equal to plus equal to 2 rands. A careful examination of the details of averaging over the rapid spatial variation, see Appendix B, indicates that the particle experiences an average force, F, given by the leading term in 61, with R given by 23, and A by 39, F can then be written in Newton's law form with no adjustable parameters required, F, gm2r2. This derivation of Newton's law, which expresses gravity as a van der Waals force, is thus the third and final result derived from the Zitterbewegung model. Sixth discussion. We begin our discussion by reiterating the logic flow of the approach pursued here. The basic thesis is the Sakharov proposal that gravity is not a separately existing fundamental force, but rather a residuum force derived from zero-point fluctuations of other fields, in the manner of the Casimir and van der Waals forces. Particularizing this hypothesis to the ZPF of the vacuum electromagnetic field, we identify the gravitational force as the van der Waals force associated with the long-range radiation fields, as opposed to the usual shorter-range induction fields generated by the Zitterbewegung particle, parton, motion response to the ZPF of the electromagnetic field. The steps in this identification are 3. First, particle mass is defined as the internal, that is, unobserved kinetic energy of Zitterbewegung motion. Its value is set by a radiation damping constant I intrinsic to the particle, in conjunction with the value of the universal cutoff frequency. Second, the value of the cutoff frequency is determined by the equivalence principle. This principle sets a requirement that an expected additional contribution to the free space Lorentz frame ZPF spectrum, viewed from an accelerated frame, is to be equated to a similar contribution expected in an unaccelerated frame, but in a gravitational field, that is, near a particle performing Zitterbewegung motion, and thereby generating a mass term. Third, a straightforward calculation of the long-range van der Waals force associated with the radiation field, correlated motions of such particles, whose parameters are determined by the above 2 steps, leads to Newton's law with no free parameters to be fixed. With a detailed theory in hand, certain attributes of the gravitational interaction become explicable in fundamental terms. As mentioned earlier, the relative weakness of the gravitational force is due to the fact that the coupling constant determined by 40 g me3h reflects as the inverse square the high value of the ZPF cutoff frequency. With regard to the attractive nature of the force, this is simply a reflection of a property typical of van der Waals forces in general. The fact that gravitational interaction is characterized by a unipolar, single-valued charge, mass, can be traced to a positive only kinetic energy basis for the mass parameter. The lack of shielding effects in gravity can also be comprehended on a rational basis. As understood here, this is a consequence of the fact that ZPF noise, quantum noise, in general cannot be shielded, a factor which in other contexts sets a lower limit on the detectability of electromagnetic signals. Specifically, in the case of ordinary electromagnetic shielding, macroscopic materials constitute dense boundaries that substantially alter field distributions, with shielding one consequence. In the gravitational case as modelled here, however, matter constitutes a dilute particle gas in an essentially high-frequency Hohlraum. As a result, particles ZPF interact. 2340. H. E. Puthoff. 39. Chance have negligible effect on the overall field distribution, hence a lack of shielding, while nonetheless permitting particle-particle interactions that lead to an attractive potential. In addition, implicit in the development pursued here are issues that extend beyond the gravitational interaction, such as mass renormalization and possible ZPF-induced contributions to the binding forces within the nucleus. However, of the many inferences that can be drawn from this study, the most important is simply the fact that it is possible to carry through the basic Sakharov program, namely, to uncover a basis for gravity in the ZPF of other non-gravitational fields. In particular, we have been able to explicate a first-order model 32 based on the ZPF of the vacuum electromagnetic field alone, once we take into account its effects on particle motion. The model thus details an electromagnetic basis for gravity. Assuming the model is a proper representation of the gravitational interaction, the already unified aspect of the model would seem to mitigate against canonical attempts at unification of gravity as a separate force, or quantization of gravity as a separate field, in favor of a viewpoint more aligned with that presented here. It is therefore seen that a well-defined, precise quantitative argument can be made that gravity is a form of long-range van der Waals force associated with particle Zitterbewegung response to the zero-point fluctuations of the electromagnetic field. As such, the gravitational interaction takes its place alongside the short-range van der Waals forces and the Casimir force as related phenomena which emerge from the underlying dynamics of the interaction of particles with the zero-point fluctuations of the vacuum electromagnetic field. Acknowledgements. I wish to express my appreciation to Professor H. Yilmaz for encouragement and useful discussion regarding the pursuit of ZPF concepts. I also wish to thank Professor Arueda of the University of Puerto Rico for helpful correspondence and for providing useful reference materials on early ZPF studies. Finally, I am indebted to G.W. Church Jr. for invaluable collaborative discussion throughout this effort. Appendix A, Dimensional Reduction Factor for Coupling Constant. As discussed in SEC. 5. The attractive force between particles derives from coupling between ZPF-induced dipole motions of the particles involved. The nature of the coupling is simplified somewhat in that the coupling takes place only between corresponding components of the motions of the two particles, that is, between and PBX-PA and PA and PA and P. This can be seen in the form taken by 43 and 44, in the derivation which leads to expression 56 for the interaction potential U, reference to the original derivation in Ref 27, shows that the potential is proportional to the quantity, plus 3 plus 2, where n, etc. are is given here in 46 and 47. That derivation assumes full three-dimensional motion, with a coupling to Pax P2, pay, and as to by. For the two-dimensional Zitterbewegung motions posited here, however, we may for convenience analyze the couplings on the basis of assuming a random distribution of 1/3 each of x-oriented dipoles, yz motion, y-oriented dipoles, xz motion, and z-oriented dipoles, xy motion. For two x-oriented dipoles, both y and z motions couple, yielding a contribution proportional to plus for an x-oriented dipole, pz motion, coupling to a y-oriented dipole, xz motion, only the z components couple, leading to a contribution proportional to, and so forth. For the 9 possible dipole pair combinations, straightforward enumeration of the possibilities leads to an average coupling factor proportional to 4 square meters plus 4 plus 4 square meters and equal to 4 n2 plus n2 plus m2. As a result, for the two-dimensional motions of interest here, a reduction factor of is to be applied to the value of the coupling constant obtained for the general three-dimensional case without constraints. Appendix B, Average Force. In the Zitterbewegung model of gravity, the two-particle interaction potential based on the radiation field van der Waals effect is given by 57 repeated here. U equal to minus 21. Cos, 2 rands, R3 2 Sinia RR. As seen, this expression can be factored into two parts, one with a slow spatial variation, 1 R, and one with a rapid spatial variation, on the order of the Planck wavelength. Sin R of interest in the gravitational interaction is not the rapidly varying component, but rather an average value, averaged over a distance large compared to the Planck wavelength. With the potential given by B1, the normalized force is given by J equal to R2 AR1, cos2 R3. As particle separation changes by an amount r, the corresponding change in potential is given by R plus AR FDR plus AR1 cos2 rands Dr. RR31 cos2 rands R plus cos2 R plus AR R plus AR 3 B3, assuming integration over a full cycle of the Planck variation so that cos 2 R plus AR equal to CO's 2 rands, and recognizing that AR, so that R plus AR equal to R plus 3 Ra, we find that B3 simplifies to 2R39, gravity as a zero-point fluctuation force. 2341, the change in potential, integrated over a cycle, is seen from B4 to be sensitive to where in the cycle, 0 to R1, the integration was begun. The average change in potential is therefore determined by averaging over the range of possible initial starting points within the cycle, namely n less than or equal to n plus 1, where n is an integer n. By reference to standard tables of integrals, we find, using B4 equal to YR2 1 rand plus 1, 2YR, 2 COS, 2 rands, 3 plus sin, 2R, SOS, 2 rands, 2R, 2R plus 2 rands plus 3x3, 5x, plus 1. Substitution of the limits of integration, with the recognition that n greater than 1 implies that n plus 1 equal to n3 plus pn then leads to O, Ya2yr, tn2, 2, 3, 2, plus pe 31, 51. But the term in large parentheses is recognized to be sin, 2 times equal to 0, so that Au becomes OU, Ya2, from which the average force can be calculated as F R RR2, F equal to 7 equal to #RE. C.W. Misner, K.S. Thorne, and J. O. Wheeler, Gravitation, Freeman, San Francisco, 1973, pp. 417 to 428. 2 degrees Celsius. W. Misner, K.S. Thorne, and J. O. Wheeler, Ref. 1, pp. 426 to 428. 3 A.D. Sakharov, Dokal, Akkad, Naux SSR, SOV, Phys. Dokal, 12, 1040, 1968. These include the following: Sakharov's own conjecture that the Lagrange function of the gravitational field is generated by vacuum polarization effects due to fermions. A.D. Sakharov, Theo, Math. Phys. 23,435, 1975. The generation of gravity as a collective excitation of fermion-antifermion pairs. Kayakama, Ichikashige, Tematsuki, and H. Terazawa. Prog. Theo. Phys. 60, 868, 1978. Proof that curvature can arise from the quantum fluctuations of pure gauge fields. B. Haslacher and E. Motolo. Phys. Let 95 billions 237th 1980. The generation of gravity as a symmetry-breaking effect in quantum field theory, in which a dynamical scale invariance breaking is postulated to take place at energies near the Planck mass. A Z. Phys. Reverend Let. 42, 417, 1979. Phys. Reverend D. 23858, 1981. Pregeometric models in which the Einstein action and metric are generated from quantum fluctuations of matter fields. Diamati and G. Veneziano. Phys. Let. 105 billions 358, 1981. S. Yoshimoto, Prog. Theo. Phys. 78,435, 1987. 5 seconds. Adler, Reverend Mod. Phys. 54,729, 1982. In this review, particular emphasis is placed on the case of renormalizable field theories with dynamical scale invariance breaking, in which the induced gravitational effective action is finite and calculable. In the terminology of gravity as a symmetry breaking effect, equations of this form are an immediate consequence of a postulated dynamical scale invariance breaking that is assumed to take place near the Planck mass energy. For details, see a Z, Ref 4. In the sense that gravity as a non-Minkowskian curvature effect can be treated in first approximation as a Newtonian force in flat spacetime, so can it be treated as a van der Waals type force in flat spacetime. And it is this basic concept that is addressed here. Although beyond the intended scope of this paper, an intimate connection between flat spacetime van der Waals and Casimir effects and vacuum curvature effects can be traced as a problem in the restructuring of vacuum energy, as in B. S. DeWitt, Phys. Rep. 19295, 1975, especially pp. 303 to 308. Thus the connection between a flat space-time approach and gravity as a curvature effect can be established as in general relativity generally. Although the approach taken here is to assume the reality of the ZPF of the electromagnetic field, for completeness we note that an alternative viewpoint posits that the results of field-particle interactions traditionally attributed to ZPF can also be expressed in terms of the radiation reaction of the particles involved, without explicit reference to the ZPF. See P. W. Maloney, in Foundations of Radiation Theory and Quantum Electrodynamics, edited by a Oberroot, Plenum, New York, 1980, Phys. Reverend A. 25, 1315, 1982. The interrelationship between these two approaches, ZPF, radiation reaction, can be shown to be complementary on the basis of an 2342, H. E. Puthoff. 39. Underlying fluctuation dissipation theorem. For further discussion of the SED approach, see, for example, H. E. Puthoff, Phys. Reverend D. 35, 3266, 1987, and references therein. Specifically, for a detailed description of the correspondence between this approach and QD treatments of linear dipoles plus radiation field systems, see P. W. Maloney, Phys. Rep. 25, 1, 1976, especially AP 71 to 78. See also reviews of SAD by T. H. Boyer in Foundations of Radiation Theory and Quantum Electrodynamics, edited by a Oberroot, Plenum, New York, 1980, L. de la Peña, in Proceedings of the Latin American School of Physics, Cali, Columbia, 1982, edited by B. Gomez et al., World Scientific, Singapore, 1983. 10 E. Im. Lifshitz, J. X. Parv. It, too, Phys. J. 1853, 1956. It. W. Marshall. Nuovo, Cimento, 38,206, 1965. 12. T. H. Boyer, Phys. Reverend D. 11,790, 1975. 13 trillions. H. Boyer, Phys. Reverend A. 5, 1799, 1972. 6. 314, 1972. 7. 1,832, 1973. 9. 2,078, 1975. 11. 1,650, 1975. T. H. Boyer, Phys. Reverend 182, 1,374, 1969. 15. T. H. Boyer, Phys. Reverend D. 21st, 2,137, 1980. See also J. S. Kim, K. S. So, S. K. Kim, and J. H. Yi, Phys. Reverend D. 36, 3,700, 1987, 16 P. C. W. Davies, J. Phys. A. 8, 609, 1975, 17 W. G. Unruh, Phys. Reverend D. 14,870, 1976, 18 in a later paper. T. H. Boyer, Phys. Reverend D. 29, 1089, 1984. Boyer shows that under the usual low-frequency peaked resonance approximation, the additional density of states factor cancels out, with the result that to this order of approximation gravitational effects are neglected. As will be shown in SEC 3, however, it is in the emergence of high-to-frequency behavior, where the additional density of states factor remains operative, that gravitational effects have their origin. 19 K. Huang, M. J. Phys. 20479, 1952. 20 A. Rueda, Phys. Reverend, February 23, 2020, 1981. 2. The possible existence of a cutoff in quantum theory is recognized to introduce a non-Lorentz invariant factor in that detection of a Doppler-shifted cutoff frequency by a moving detector, in principle, reveal absolute motion. As pointed out in the literature, however, for example, by M. Ashoup, A.M., J. Phys. 53, 122, 1985. As long as the cutoff frequency is beyond detectability, as is the Planck frequency in this case, there is no measurable consequence expected of such a breakdown of Lorentz invariance at this limit of present physical theory, either now or in the foreseeable future. 22. See, for example, W. Heitler, The Quantum Theory of Radiation, 3rd ed., Oxford University Press, London, 1954. pp. 293, f. 23. Bohm, The Special Theory of Relativity, Benjamin Cummings, Reading, Ma, 1965, chap 1924. The particle mass given by 23 equal to Re3 corresponds to a renormalized or dressed mass, and it is this mass, of dynamical origin, that appears in the field, generation effects, and interaction potential corresponding to gravity. If one wished to do so, the derivation that led to 23 would permit one to extract an unobserved harmonic oscillator bare mass μ, which appears in the definition of I preceding 8. This unrenormalized mass is given by the large value μ, m, where mp, hc, g is the Planck mass. Although unobserved experimentally, it is this unrenormalized mass O which could be said to interact at the level of the ZPF. Viewed in the usual QED terms, its value is so high and its Compton wavelength so small as to justify its treatment as a point particle, as we have done, even at wavelengths corresponding to the ZPF, Planck, cutoff frequency. Lacking any apparent dynamic origin or interaction effects at an observable level, however, the concept of a bare mass can be seen to be simply an inference derived from the particle parameter 1, which appears to be the operative parameter of significance. Therefore, questions as to why the bare mass does not generate a large gravitational field, which can be taken to be related to the well-known field-theoretic conundrum as to why the vacuum zero-point energy does not do likewise, find a simple solution in the Sakharov approach, as pursued here. In the dynamics of the model, the only gravitational fields found to emerge from the analysis are those that are in fact observed experimentally, and this is one of the strengths of the approach. 25. See, for example, J. A. Stratton, Electromagnetic Theory, M.C. Graw-Hill, New York, 1941, p. 435. 26. C. T. H. Boyer, Ref. 12. Appendix B27, Trillions. H. Boyer, Phys. Reverend 7, 1832, 1973, 28 trillions. H. Boyer, Ref. 27, EQs, and 57, 29. The complete expression, including both radiation and induction field terms, is given by 92 in Ref. 27. It is, in our units, and for W20, 9 U redu R3 do I56 plus HR WR33 R. This constitutes the general expression for the retarded van der Waals forces at all distances. While the first, radiation field, term in large parentheses, is found here to account for the long-range gravitational interaction, the remaining short-range, induction field, terms have yet to be investigated with regard to their contribution to binding at the nuclear, parton, and nucleon level. J. Wren, 53,193, 1971. 30 millions Physica, 3 hours. B.G.D. Polder Phys, Reverend 73,360, 1948. Casimir and 32, further development of the model could include, for example, extending Paarten-Zitterbewegung to the relativistic case. 33. See, for example, H. B. Dwight, Tables of Integrals and Other Mathematical Data, Macmillan, New York, 1961, especially E's. 441.14 and 431.11.